Assalamu alaikum students. Welcome to our another online session for the course Computer Organization. And in today's session, we will be discussing the cache performance, how we're going to measure the cache performance. And in the previous session, we have just got the introduction to the cache memory, and we've seen different types of memories which we can use in a computer system. And we've discussed about the direct map cache in detail, but in today's session we will be discussing about the performance parameters and how the other types, the associative and fully associative cache memories are implemented in the computer system, and what are the benefits and limitations for that. So to start with our discussion, first of all, let us see what are the crucial components that we have to consider while defining the performance of the system. And in the previous session, we've discussed about the CPU time or the execution time basically depends upon two factors. One are the number of CPU cycles that are dependent upon the instruction count multiplied by cycles per instruction, that was the CPI term, multiplied by clock cycle time or divided by the clock frequency of the processor. But here in this formula, we haven't considered any sort of the memory stall cycles were not considered, and in this formula was valid in a scenario when memory stall equals to 0. There is no memory delay. Memory stall cycles are equal to 0. But what if the case we have the main memory and we do have some stall cycles? Then we have to refresh our CPU execution time formula. So in that we have to add the memory stall cycles inside the execution time basically in order to compute the effective CPI to determine the total execution time of the system. So what the major components of the CPU time basically are the program execution cycles, basically that includes the cache hit time, and the memory stall cycles, basically that includes the cache misses. So with simplifying assumption, we can say that the memory stall cycles are equal to how many memory accesses we have in a program. For example, we have a program and that have 100 instructions, and there are 30 instructions that require the memory accesses, which means that 30 of the instructions are load word and store word instructions. So the proportion of those instructions multiplied by the miss rate and multiplied by the miss penalty, that determines our memory stall cycles. So the number of accesses per program that are equal to the instructions per program, that is basically your instruction count multiplied by how many misses we have generated per instruction, that is important, and multiplied by the miss penalty, right? So let's consider an example in which we've got two different cache memories. One is for the instruction cache and one is the data cache. Instruction cache is accessed for the complete program. So the miss rate for the instruction cache is 2%, which means that if we access a program and it contains 10 instructions and 2 of the instructions are missed, while 8 are hit in the instruction cache. Similarly, for the data cache miss rate, that is equal to 4%, and data cache with this rate was only applicable for that time duration for those instructions that require the data memory access. Otherwise, that is not considered. So data cache miss rate is 4%, and if you see that 36% of the instructions are loads and store, which means that for 36% instructions, we have 4% miss rate in the data. So first of all, let us compute the other parameters are the miss penalty, that are the 100 clock cycles in case of if we got a miss, either it's instruction or data. 100 CPU cycles are wasted, or 100 clock cycles of the processor are wasted, and the base CPI or the ideal cache is 2. So what we have to do is we have to compute the CPI for the system that has, or the effective CPI of the system that has that uh, cache miss basically incorporated in with. So we have to compute the effective CPI. Since rest of the parameters are same, effective CPI basically depends upon the instruction cache misses and data cache misses. What we have to deal with that, and we have to add that, and depending upon the proportion. So that would be equal to 2% for the instruction cache multiplied by 100. So that are the miss cycles per instruction for the instruction cache, and for the data cache we've got what we are doing there is that we've got 36% of loads in store, so 0.36 multiplied by the miss rate of the data cache memory, that is 0.04, multiplied by 100 clock cycles, that is equal to 1.44. So for the actual CPI, basically we just have to add the instruction cache stalls and data cache stalls, or the miss cycles per instruction, you can say that. So that is equal to 2. And definitely there, this is added with the base CPI. So base CPI was 2, and these are the additional clock cycles per instruction that are being consumed. So the actual CPI of the system is basically 5.44. And if you consider the performance here, that is the execution time of the actual system divided by the execution time of the base system, we can say that the base system is 2.72 times much more efficient as compared to the system with more stalls. So the ideal system is basically 2.72 times more faster or efficient as compared to the system, the actual CPI of the actual CPU that has that proportions of misses with load and store instructions. Now, what is the average access time basically? So average access time is dependent upon the proportion of hit basically. So hit time is also important for the performance. So how many accesses we got hit, that determines the hit time basically. Plus those which aren't basically hit, basically those are the misses or the miss instructions. So we have to multiply the miss rate with the miss penalty, and we have to add that time with the hit time. So that is the average access time in order to access any block or data from the memory, either it's a hit or a miss. So consider an example that CPU has a clock period of 1 nanosecond. So clock cycle time is basically 1 nanosecond. Hit time is 1 cycle, and miss penalty is 20 cycles. So an instruction cache miss rate is 5%. So we're computing for the instruction cache. So average memory access time is equal to 1 and multiplied by miss rate, that is 0.05, multiplied by miss penalty. So that is 2 nanoseconds. So 2 cycles per instruction are being consumed if you have to access the memory. Now coming to the performance, basically in the cases if we've got lesser misses, the CPU performance is increased, and miss penalty becomes more significant in that particular scenario. So what we could do is we could decrease by decreasing the base CPI, so that we can spend a greater proportion of time on memory stalls, and increasing the clock rate. Memory stall accounts for more CPU cycles, and we can't neglect cache behavior when evaluating the system performance. So these are the key factors that basically determine the performance of the system. Now coming to the associative cache memory, basically for the direct map cache memory, we've said that the correspondence of the blocks with the cache locations are 1 to 1, and each block has a fixed location, and block cannot reside other than that location. But a fully associative cache, basically that gives you the liberty to save the block at any available location that you desire. So the restrictions in the direct map are totally eliminated while discussing the fully associative cache. So allows a given block to go in any cache entry. So requires all entries to be searched at once, and comparator per entry. So this is just the expensive mechanism, as we require comparators to search each entry. But this gives us the liberty to save the block at any location in the cache, rather than we are restricting that this block should can reside only at that location. So coming to the n-way set associative cache, basically, so set associative cache is in between the direct map and a fully associative cache. So what we do is we distribute, or we make the sets in our cache memory. So cache memory is distributed in sets, and each set can have the specific location, and the block is mapped to the set in a direct mapped manner, but within that set the block can go anywhere. So we are combining the properties of direct map and fully associative in order to implement the n-way set associative. For example, n can be 2, 4, 8, 16. So for example, if n is 2, which means that in a set In a set we can store two blocks. In a set we can store block A, for example, and block B. If n is 4, so within a set we can store four blocks A, B, C, D. For example, we got these four blocks A, B, C, and D, and so on and so forth. So n would always be in 2 raised to power n notation. Or the number of blocks in the set are basically are always in 2 raised to power n notation. We cannot have a set of 3 locations. We cannot have set of 7 locations, and so on and so forth. So each set contains the n entries, and the block number determines which set basically. So what we have to do is we have to do take the modulo operation with the block number with the number of sets in a cache. So this sort of mapping is known to be the direct, but within that set, that particular block can reside in any location. For example, we've got a block X that is mapped to this particular set. So this X can either be stored at this location or it can be stored at this location. It can go anywhere. So we have to search all entries in the given set at once. So n comparators are required, and it's less expensive as compared to the fully associative cache memory. Now this is the example for the direct map cache and the set associative and fully associative cache. And you can see that for the direct map cache, it can go on a specific location depending upon which for which it is mapped. In the set associative, basically we have distributed the memory into the cache. So we've got these sets, and each set has, for example, this is the example of two-way set associative. We've got two locations in a set. So, for example, this particular block is mapped to set 0. So at set 0, it can go in either this location or it can go in this location. So there is no restriction for that. So whatsoever the location is free, we can save that within that particular set. But we cannot map this block into set number 1 or set number 2 or set number 3. But for the fully associative, we've got liberty that it depends upon the nature of the block and the system that the block can be randomly placed at any location, any available location in a cache memory. So you can see that the orientation for the cache memory with 8 entries for the direct map, associative, and set associative cache. In a direct map cache, we've got 8 separate locations. In a set associative cache, since we've got the locations that are distributed into the sets basically, so each set states can contain multiple blocks. So for the two-way set associative, we can store 2 blocks in a set. So total number of sets, we've got 4 sets. And for the four-way set associative, we can store 4 blocks in a set. So we get 2 sets for the same 8 entries, and 4 number of blocks can be resided in those locations. And for the 8-way set associative, it's just like the 8 consecutive locations in which we can store any block at any particular location. Now coming to the associativity example, for example, in this particular scenario, we've got a 4 block cache. So the total number of blocks in a cache are 4 basically. So for the direct mapped cache and for the set associative 2 and for full associative, let us see what are the hits and miss basically. So for the direct map cache basically, if you see that the block address 0 that can reside at the cache index 0, and this is a miss. For the first time 0 is missed, so 0 is placed at that particular location. For the next axis of 8, this is also a miss, that is also placed in the location. And for the next 0 block basically it's already there, so that would be hit in the memory at that time instance. And later on for the 6 and 8, we're gonna see that either the block is residing in the memory or not. So same is the case for the two and the fully associative caches. You have to go through this example, and if you got any query, we can discuss that in our discussion sessions. Well, that was all for this session. Let me see. Uh, yeah, that's all for the today's session, and in the later session we will be focusing on the storage basically, and we will be discussing RAID basically and the levels of the RAID in detail and with some examples.